Okay. So welcome everybody. Thank you very much for connecting. So this is the Informs Quality and Statistics and Reliability section speaking, where our goal is to promote interaction among scholars and practitioners in quality, statistics, and reliability. And we have a strong emphasis on research and real-world applications. And we are very proud to say that we have several members, well, many members around several countries, all interested in quality, statistics, and reliability. So this initiative and this tutorial that you are about to take is part of one initiative from the Council on Quality Statistics and Reliability to deliver tutorials, broad tutorials on several topics. And today we are joined by Dr. Peter Goos, whose topic is about OMARS designs, small response surface designs for product and process optimization. But before formally introducing Dr. Peter Goos, let me just give you just some information that you can join the QSR session. So if you are already an Informs member, you can go to this link. I will put it on the chat in a moment. And well, there are some fees that you can pay in order to join the QSR. But also we have the other option that if you are not an Informs member, you can also email Francis in order to get your subscription for $25 per year. So benefits of becoming a member is being part of this network, also the events that we are regularly organizing, and well, just actively participating in all these events, and also collaborating with other people from industry and also from academia. All right, so let me stop sharing. So today we have the second tutorial by Dr. Peter Goos. So he is a full professor at the Faculty of Bioscience Engineering of the University of Leuven and at the Faculty of Business and Economics of the University of Antwerp. He's also the co-founder of FX, which is a state-of-the-art software for the construction and analysis of experimental design. So having said this, his main research area is statistical design and analysis of experiments with significant contributions in marketing, transportation, and operations research. He's the author of the seminal book entitled The Optimal Experimental Design, a case study approach, and has received numerous awards by the American Society for Quality, as well as other important societies. So, Dr. Peter Goos, thank you very much, and the floor is yours.
Thank you, Alan. I will first share my screen. Hopefully that works smoothly. You can see the slides right now?
Yes.
Thank you. So yeah, I'm going to talk about OMARS designs, small experimental designs for product and process optimization. And I do not know to what extent the participants in this particular workshop are familiar with experimental design. So therefore, I have created some introductory slides to introduce the concept of experimental design, why it's important and how it works. But before I dive into these introductory slides, I should point out that the contents of these slides are largely based on joint work with José Núñez Ares, who works for the spin-off of the University of Leuven called FX, which has recently been taken over by Minitab. And José is the person on the right-hand side of the picture. First of all, the context of this talk is design of experiments. And for those of you who are not familiar with design of experiments is a sub-branch of statistics that deals with defining which experimental tests we need to perform to get a good idea about the relation between multiple inputs of a system and the output of the system. So we're going to sort of perform tests concerning a system. And to do that, we will test various combinations of outputs and see what happens to the output. In more technical terms, These inputs are generally called the x's, and the output is usually called y. And so what we're going to do in an experimental plan is we're going to define which combinations of the x's we will study, and we will figure out what happens to the output y when doing so. So that's what design of experiments is about. Now, what do we want for the experimental tests that we're going to do to study that system? Well, first of all, there should not be too many tests. Otherwise, it all becomes too time-consuming, too costly. So we want to be economical in terms of the number of tests we're going to do. And of course, ideally, the tests that we can afford, they should be highly informative. So we should be able to infer from all the tests that we do which inputs have an effect on the output and which inputs don't have an effect on the output. We can also figure out what the nature is of the relation between the inputs and the outputs. That relation can be linear, it can be non-linear, but the tests that we perform should allow us to detect whether or not there is linearity. And one of the things we also like to figure out is whether the impact of one input depends on the level of another input. In statistics, we call that an interaction effect. We have interaction effects whenever the relation between the x's and the y's is somewhat complicated. In that case, it's very hard to isolate the effect of one input on the outputs. So that's the kind of things that we want to learn from all the tests. And how do we do that formally? Well, we do that generally by creating a statistical model that summarizes basically our data, the data that consists of combinations of the x's and the outputs that we have observed. That statistical model has multiple functions. First function is, it should describe very well the behavior of the system that we are studying. And second of all, it should allow us to make predictions of the outputs for any combination of the inputs, basically, in the whole space that we have studied. And once we are able to make predictions with our model, we can also exploit the model to identify optimal combinations of x's, optimal input combinations, so that we can get the desired outputs at the end of the day. So that's more or less in plain English what experimental design or design of experiments is about. I used the word statistical model here on this slide. Now, what's the typical model that we use in design of experiments, the working horse in design of experiments when it comes to modeling? Well, that's the family of linear regression models. And you have an awful lot of different regression models, but a useful one is what we call a response surface model. In a response surface model, we use this kind of relation, this kind of model where the output y is a linear combination of some betas, some Greek letters. These betas jointly describe the effects that the inputs have on the output, and the effects that the inputs have on the output can be sort of decomposed into linear effects. So here you see terms that are linear in the x's. The betas that go with these terms are the main effects, so the linear effects of the x's. Then we also have this term here with a cross product of two inputs. We call that an interaction term and an interaction effect. That's the beta here. And then we also have terms containing squares of the inputs. We call these the quadratic terms, and the betas in these quadratic terms are the quadratic effects. That's a very commonly used model. With that kind of model, you can describe the behavior of an awful lot of systems. Of course, this is an example model for two inputs, two x's. And in design of experiments, we call these inputs or these x's, we call them the factors in our experiment. And this particular model for 2 inputs has 6 different betas. So 6 unknown effects to be estimated after the experiment has been done, the experiment containing hopefully a limited number of tests. Now, of course, you can imagine that if you have more inputs to study for your system, that this model becomes more involved. There will be more main effects or linear effects. There will be more quadratic effects, and there will be more interaction effects to estimate. So the number of parameters goes up quite quickly with the number of inputs that you want to study. One very nice thing about this model is that it's computationally very easy to estimate. And it's also a sort of explainable model where you can really see the effects that the X's have on your output. Now, one technical aspect concerning this model with linear effects, interaction effects, and quadratic effects is that to be able to estimate that model, to build that model for your data.
Simplemente, ¿qué va a suceder? Tenemos.
Yeah, go ahead, Peter. I just muted the participants, so please keep your. You can raise your hand if you have questions, and then you can unmute yourself. Right.
Yeah, a technical aspect concerning this model is that we need to study every X, every input at 3 different levels at least to be able to quantify all these effects. And that requirement to have 3 levels that will become visible in the next few slides when I start discussing experimental plans and especially the OMARS designs that I will discuss. Now, historically, in design of experiments, the focus is or has always been initially on the main effects or the linear effects on the one hand, and the interaction effects on the other hand. So that's these effects here. These were priority number 1 usually. Traditional strategy was to try to quantify these effects in a so-called screening experiment. A screening experiment is usually quite a small experiment, which is very ambitious, where you want to estimate the effects of many input factors at the same time. After the screening experiments, you perform a data analysis. You can then figure out which factors of all those that you studied are really important. And then you perform a second experiment, a so-called response surface experiment, which is more detailed and which allows you also to estimate the quadratic effects of those really important factors. And of course, the second experiment, the response surface experiment, is then followed by another data analysis, which is quite detailed and which allows you to optimize your system to identify the optimal combinations of the X's that give you the desired output. That's the traditional approach. You can find it in every textbook on design of experiments. You can find it in every software that can do a design of experiments for you. The thing is that we're deep into the 21st century and more industries consider this particular strategy to be too slow. Companies want to innovate quickly, efficiently. They want to go to the market quickly. And therefore, doing 2 experiments, one after the other, that's like too slow. It's like a waste of time. And there's a movement in certain industries to combine these 2 phases, screening experimentation and response surface experimentation, into a single experiment. Now that's sort of whole new approach, a break with the tradition in design of experiments, and that break in the tradition, of course, requires a new kind of experimental plan. So new definitions of which tests to use in your experiment. And that's what this talk is going to be about. The OMARS designs in the title are suitable experimental plans to combine screening, screening, and response surface experimentation into one. Now, Of course, all of that is quite ambitious. You want a limited number of tests. You want to learn an awful lot. So that's very challenging. And because the experiments are a little bit small, yeah, you have a sort of challenge to identify the best model for your data. And therefore, you need more sophisticated modeling techniques than in the past. Basically, you need to exploit the existing computational power to identify the best possible models when you want to combine screening and response surface experimentation in one. And I'm going to talk a little bit about that sophisticated modeling at the end of this talk. So yeah, one key term that I used here was response surface experiment. Well, when you want to plan a response surface experiment, you call that a response surface design. When we use the word design, when I use the word design today, you should think of a design as a plan for your experiment, as a list of the tests that you're going to do. Well, a response surface design is intended to learn about linear or main effects, interaction effects, and quadratic effects about your input factors. Then you can model and then you can optimize your process, your product, or your system. Now, in textbooks on design of experiments, whenever you mention response surface design, it's automatically about these three kinds of effects that I showed you a couple of slides ago: the main effects, the quadratic effects, and the interaction effects. The best known experimental designs for these situations are factorial designs that study every factor at 3 levels. We call that 3 to the k full factorial designs, where k is the number of factors that you want to study. More economical experimental designs are central composite designs, often abbreviated as CCDs. And there's also Box-Painkin designs. That's also a more economical kind of response surface design than the 3 to the k factorial designs. Now, also these designs you can find in every software, in every textbook. Especially the 3 to the power k full factorial designs are, labor intensive, costly, because they involve quite a lot of tests. So that's traditional design of experiments, available everywhere, basically. Here's an example for those of you who are not yet familiar with experimental design. Here's an example of one of those designs, a 3 to the power 2 factorial design. That means we're going to study 2 inputs, 2 factors at 3 levels. And there's going to be 9 test combinations. We have 3 levels for the first input, x1, a low level, a middle level, and a high level. And we combine these 3 levels for x1 with a low level, a high level, and an intermediate level for x2, gives us 9 test combinations. 9 is still a doable number, but of course, imagine you want to study 8 input factors, then this would become 3 to the power 8, and 3 to the power 8 tests. Yeah, for most scientific studies, for most experiments in business and industry, that's totally out of the question. So clearly we need something more economical in general than these 3 to the power k factorial designs. And one more economical thing is a central composite design, for example. Central composite designs are already quite old, and they do not study every possible combination of the X's in your system. This is, by the way, a central composite design for 3 factors, x1, x2, and x3. And yeah, what you can do is you can place the red bullets on the faces of the cube, and then you also have an experimental plan with 3 levels for every x. So that's another example of a response surface design. Also, the central composite design, it's more economical for sure, but when you want to study 8 factors with a central composite design, the number of tests that you have to do also becomes quite large. So here we have classical response surface designs. These are very popular already since the 1950s, I would say. And the reason they are very popular is that they have always been easy to analyze. In the 1950s, people didn't have powerful computers. Every calculation, every estimation of these linear regression models had to be done by hand. So the designs had to have, the experimental plans had to have specific technical properties to enable that analysis by hand, basically. And these specific technical properties, they can be visualized in a color map on the correlations of the model matrix. Now, what does that color map show? If you're new to design of experiments, you might never have seen such a color map. But the important thing in the color map is that, first of all, it's about the X values that you study in your experiment. And here you can see I have 8 X's. So I created the graph for an experiment with 8 factors. If you have 8 factors, you have 28 cross products of 2 X's. So there's 28 interaction effects, and there's 8 squares of the X's, and the squares of the X's are right here. Now, whenever you have an experimental plan, you can check all the correlations between the X's themselves and between the cross products of 2 X's and between the squares of the X's. All of these are building blocks of our linear regression model. And ideally, the values of all these quantities here, the values of all these functions of the X's are uncorrelated. If these values are uncorrelated, you have a very easy data analysis that you can do by hand. And the color map on the correlations visualizes whether or not all these values here for these functions of the X's are correlated or not. The more blue such a color map is, the better, because blue indicates 0 correlation. Red indicates quite strong correlation between the X's. Well, pink means quite strong. Red means perfect correlation between certain X's. Now, what is really nice about traditional response surface designs, for example, the 8-factor central composite design, that is that the top left part of the color map is perfectly blue, except on the diagonal. The red on the diagonal is unavoidable because a certain X is always perfectly correlated with itself. But the rest of the upper left part of the color map is blue, meaning that all the X's are uncorrelated. That means that you can estimate the main effects of the factors independently from each other. So the most important effects of the inputs you can estimate independently. The upper right part of the color map is also perfectly blue. So that means that you can estimate the main effects, the most important effects of the inputs independently from the second order effects. That's also a nice technical property to have. Then in a classical central composite design, the central part of the color map is also perfect. That means that the interaction effects you can also estimate independently from each other, and you can estimate the interaction effects independently from the quadratic effects, because this part of the color map is also perfectly blue. So we have uncorrelated functions of the X's, and these functions of the X's are relevant for our response surface model. The only thing where it's not so perfect is between the quadratic effects. So there is some correlation between the squares of the quadratic effects that is unavoidable. Squares of X's tend to be correlated. But the most important news is that the majority of the color map here, the largest part of the color map, is perfectly blue. This slide summarizes all of that. Traditional response surface designs have great orthogonality properties. So the main effects are uncorrelated from each other. The X's are uncorrelated from each other. We say in the jargon that the design is orthogonal for the main effects. Also, the main effects are orthogonal to the second order effects, to the two-factor interactions and to the quadratic effects. And we've also seen that two-factor interaction effects are orthogonal to the quadratic effects here. That basically means that these traditional response surface designs, they have great statistical properties. They offer large powers, for example, for the main effects and for the two-factor interactions. That's all positive, of course. Now, what's not so positive is that the number of tests you need to perform if you execute such an experimental plan, such a traditional response surface design, the number of tests increases quite rapidly with the number of input factors that you want to study. So these experimental plans tend to be intensive, tend to be expensive. So that's a negative point. And I end this slide with another positive point about the traditional designs. Yeah, you have a painless data analysis that you can even do by hand if you're motivated enough to do that. A painful data analysis, but yeah, the downside is the cost is large. That's the traditional thing to do. Now, much more recently, since 2011, there's another kind of experimental plan that came about. And that's the so-called definitive screening design. Definitive screening designs also have 3 levels for every factor that you want to study. So these definitive screening designs, they also allow you to focus on main effects, quadratic effects, and two-factor interactions. I said 2011, that's the date where they appeared. In the literature, these definitive screening designs were invented by Bradley Jones and Chris Nachtsheim, 2 famous researchers in design of experiments. A year later, a triplet of Chinese researchers found an easier way to construct the definitive screening designs based on so-called conference matrices, special square matrices from combinatorial mathematics. And since the appearance of the paper by the triplet of Chinese authors, definitive screening designs are always constructed using these conference matrices in commercial software. Now, what do these definitive screening designs look like? Well, here's an example. And I again took an 8-factor example. So you see 8 X's again. And you can see 17 rows in the table here. The 17 rows in the table are the 17 test combinations that belong to the definitive screening design. There's a specific structure in all the test combinations here. You can see, if you look closely, that the first 2 rows are each other's opposites. The 3rd and the 4th row as well, they're also each other's opposite. The 5th and the 6th, the 7th and the 8th, and so on, are also each other's opposite. And also rows 15 and 16 are each other's opposite, as you can see. We call these mirror image pairs or fold-over pairs. Definitive screening designs are made up of fold-over pairs. And there's a very specific pattern in the zeros, as you can see. So in the first column, the zeros appear in the first 2 rows. In the second column, the zeros appear in rows 3 and 4. We have the zeros marching down basically the diagonal of this matrix. And the final thing is that A definitive screening design always has a row of zeros, meaning that there's one test that we have to do at the intermediate level of all the inputs. And by the way, for those of you who are not familiar with design of experiments, whenever I show a -1, I mean that we study the input at a low level. Whenever I show a +1, it means we study the input at a high level. And whenever there's a 0, we study the input at an intermediate level. So you can see there's a very specific structure for a definitive screening design. Now, what is the color map for a definitive screening design? Well, here it is. And you can immediately see, of course, that the color map is substantially less blue for a definitive screening design than for a traditional response surface design. But there's some good news. The top left corner of the color map for the definitive screening design is also perfect, meaning that a definitive screening design also allows you to estimate the main effects independently from each other. The top right corner is also blue, so that means that you can estimate the main effects independently also from the second order effects with a definitive screening design, just like in a traditional response surface design. But that's where the good news stops. The central part of the color map in a definitive screening design is far from blue. And for this particular definitive screening design, you can see some pretty dark pink, meaning that there's quite a lot of correlation between the interaction effects when you execute this particular definitive screening design here. That means that you're going to have trouble to estimate interaction effects. You're going to have trouble to get precise estimates of the interaction effects. Also, the rest of the color map is not perfectly blue, as you can see. But I would say the biggest problem for this particular color map is the central part with substantial correlation between the interaction effects. To summarize, well, definitive screening designs also have nice properties. The main effects are also orthogonal to each other, so we can estimate them independently. They're orthogonal to the two-factor interactions and to the quadratic effects, which is very similar to the traditional response surface designs. And because of these technical properties, you can call the definitive screening designs minimally aliased designs. So because the main effects are orthogonal to the two-factor interactions and to the quadratic effects. But we've seen that there is quite a lot of pink in the central part of the color map. So that means that there is not so good news for the two-factor interaction effects, because they are very strongly aliased with each other. And in some definitive screening designs, the interaction effects are also pretty strongly correlated with the quadratic effects. So sometimes there's more pink in the color map than in the color map that you've just seen. So you can see there's good news. First, solid bullets. There's some bad news as well in the second and third solid bullet here. On the positive side, that's why experimenters like definitive screening designs quite a lot. Definitive screening designs require you to do only a limited number of tests. Remember, the definitive screening design that I showed you had 17 tests. That's 2 times the number of input factors plus 1. And because of that formula, 2 times the number of input factors plus 1, the required number of tests increases only linearly with the number of factors when you use a definitive screening design. So you can say that definitive screening designs are very economical experimental plans. By the way, if you would want to do a central composite design for 8 input factors, you would need at least 45 tests, which is substantially more, of course, than the 17 tests that you have to do according to the definitive screening design. Another thing that I can say about these definitive screening designs, which are liked a lot because they are economical, is that quite often these definitive screening designs, usually abbreviated as DSDs, these definitive screening designs are sometimes sold as a screening design and a response surface design in one. And yeah, why is that? Well, if you're in the lucky situation that of all the input factors that you've studied, only a few really matter, these definitive screening designs, they actually become a very good response surface design in the few factors that really matter. And I must say that in the history of design of experiments, it has often been the case that only a few factors really matter, even when you study quite a lot of factors. Recall that the factor sparsity principle that is active in design of experiments. So because of that, technical property of definitive screening designs, they are nowadays viewed a little bit as the smallest kind of response surface designs that you can perform. But I should immediately add a warning to all of that. It's of course very ambitious to study a lot of input factors with just a limited number of tests. Well, if you try to do that, you're almost guaranteed to have quite a painful data analysis where, even when you do your best to do the most sophisticated data analysis, you will often be left with some ambiguity regarding which model is best, regarding which interaction effects matter the most, which interaction effects matter the least. So definitive screening designs are economical, but the data analysis will not always be smoothly. And the pink cells in the color map don't help for that. Another thing that I can say about the definitive screening designs is that they only exist for a limited number of factors, for a limited number of tests. So there's not an incredible lot of flexibility when it comes to picking a definitive screening design. So that was a long introduction about everything that existed already quite a while. The traditional response surface designs have existed since the 1950s, and we've seen that they have very attractive technical properties, but they require you to do a lot of tests. On the other hand, we have the definitive screening designs, which are more recent. They are economical, so they only require you to do a small number of tests, and they have some attractive properties, but also some unattractive properties that make the data analysis more painful. Now, in between the traditional response surface designs and the definitive screening designs, there's a sort of gap. So we wondered, and that's Jose, whose picture I showed in the beginning of the presentation, Jose and I, we wondered whether there were possibly some experimental plans that exist with similar technical properties and intermediate number of tests. So we were especially interested in experimental plans with a little bit more tests than the definitive screening designs, but substantially fewer tests than response surface designs. And we wanted intermediate numbers of tests because we want, at the end of the day, to have a less painful data analysis, a data analysis that hopefully does not leave us with a lot of ambiguity about which input factors matter and which input factors don't matter. Well, we discovered a whole new family of experimental plans that basically fills the gap between large response surface designs on the one hand and small definitive screening designs on the other hand. And the gap I mentioned is visualized in this slide. In this slide, we have the number of factors on the horizontal axis. We have the number of tests you have to perform on the vertical axis. And we have 3 lines in the graph. The blue line is for the central composite design. The gray line is for the Box-Beinken design. And the yellow line is for the definitive screening designs. The first 2 lines are the traditional response surface designs. The yellow line is the more modern definitive screening design. And you can see that the number of tests you have to perform according to a definitive screening design only creeps up slowly as the number of factors goes up. But the traditional response surface designs have a number of tests that increases very rapidly with the number of factors. And in between the definitive screening designs and the traditional response surface designs, there is this big gap that we filled with that new family of experimental plans. And we call these new experimental plans OMARS designs. OMARS is an acronym which stands for orthogonal minimally aliased response surface designs. That's quite a long thing to pronounce. OMARS is, of course, much shorter, perhaps easier to remember. We call the OMARS designs RS, response surface designs, because they have 3 levels for every input factor, so that we can quantify main effects and interaction effects and quadratic effects, just like in a traditional response surface design. We call the OMARS designs orthogonal because the main effects are uncorrelated with each other, just like in these traditional response surface designs as well. So that's where the O comes from. And the final technical property is that the main effects are orthogonal to the 2-factor interactions and to the quadratic effects. And in the experimental design literature, that property is called minimal aliasing, MA. So we have orthogonal O, minimally aliased MA, response surface RS designs, so OMARS designs. In our very first paper on the topic, all of our OMARS designs have yet another technical property, and that is that every main effect can be estimated equally well with our initial OMARS designs. So we have the same precision of estimation for all the main effects. Yeah, and we call that a uniform precision property. I will explain in a minute how you can recognize whether an OMARS design has a uniform precision property, yes or no. In our very first paper published in Technometrics a couple of years ago, we have this particular table that shows how many OMARS designs we discovered initially. Our initial work was for experiments with 3, 4, 5, 6, and 7 factors. And we studied experimental plans with these numbers of tests, 8 to 14 tests for 3 factors, 14 to 70 tests for 7 factors. So that's the kind of things we tried out. And the third line of this table this particular line shows how many of these uniform precision OMARS designs we discovered at the time. You can see that the more factors you want to study, the more different OMARS designs exist. And I should highlight, or I should point out, that in our very first published paper about that topic, we ran into computational difficulties for 6 and 7 factors. So our enumeration, our search for OMARS designs was not complete at the time. So you can already see that we found quite a lot of new experimental plans in the very beginning of our investigation of this topic. How did we find these OMARS designs? Well, for a public that belongs to Informs, I should not hide that. We used integer linear programming techniques to find the OMARS designs. So for every number of tests we wanted to study, we set up a system of linear equalities, the solution of which is an OMARS design. So we solved that system of linear equalities to get one OMARS design. And then we solved the same system of linear equalities again with some additional constraints in it, so that next time we solve the system of linear equalities, we find a different OMARS design. So we did that repeatedly, over and over and over. We solved that system of linear equalities, and every time we found a new OMARS design for a particular number of tests. And at some point in time, you get your solver reports that there's no more feasible solution. And then you know that you've found all the different OMARS designs that exist for a particular number of tests and a particular number of factors. That's the system of linear equalities. I will not discuss that system in detail today. You can read all about it in the Technometrics paper from a couple of years ago. So we found quite a lot of OMARS designs back then. Now, it's not because you find a lot of OMARS designs that you have good experimental plans. Of course, in the paper, we had to prove that the OMARS designs had good statistical properties. And yeah, one little example in the paper, I also included in the slides today. In the slides, I compare an OMARS design with 22 tests for 5 factors, also reported in our paper. And we compare that particular experimental plan with a definitive screening design extracted from the JUMP software. And we constructed the definitive screening design in such a way that it also has 22 tests for 5 factors, so that it's an honest comparison of 2 experimental plans for 22 tests. Now, the OMARS design immediately had one important advantage. With the OMARS design, we can estimate all the interaction effects at the same time, while that was not possible with the definitive screening design. The OMARS design also had better projection properties. So that means that the OMARS experimental plan allows you to estimate more different models with 2 factors, with 3 factors, with 4 factors, which we also like. And the OMARS design also allows you to estimate quadratic effects substantially better than the definitive screening design, at the expense of a slightly lower precision for the main effects. This picture visualizes the strengths of the OMARS design compared to the definitive screening design. In this picture, on the vertical axis, you see the power. the power in design of experiments, that's the probability that you will discover an existing effect. Well, you can see that the blue bars in this graph, which corresponds to the OMARS design, the blue bars in this graph are substantially larger than the purple bars, which are the powers for the definitive screening design. So for the quadratic effects, the OMARS design does much better in terms of power. And this is at the expense of a slightly lower power for the main effects, as you can see. So that's another indication that the OMARS designs can be very valuable. And I could make a similar picture for the interaction effects, but I did not include that particular picture in the slides. What I did include in the slides is the color maps for the OMARS design in our paper on the left, and definitive screening design, which we extracted from the JUMP software. And you can see that in the color map for the definitive screening design, we have quite a bit of dark pink, which we don't like. And we do not have this kind of dark pink in the color map for the OMARS design. So in any case, that shows that the new family of designs has the capability to be better or to compete with designs that already exist, even the small designs, the small definitive screenings. And here you can see the 22 test combinations from the OMARS design. 22 test combinations again involve -1s, 0s, and +1s, referring to the low level, the high level, and the intermediate level of the 5 input factors. The design that you see here also involves fold-over pairs, just like the definitive screening design that I showed you a couple of minutes ago. You can see that the very first test in the OMARS design is the mirror image of the last test. The second test is the mirror image of the one but last test, and so on and so on. The 2 tests in the middle of the experimental plan are also each other's opposite. So we have the very same technical property. Design also involves as many +1s as there are -1s. That's inevitable if your plan is a fold-over plan. There's no center runs, so no test is done at the 0, 0, 0, 0, 0 combination. And if you would check the entire experimental plan, you would see that there are 6 zeros in every column. And because the number of zeros in every column is exactly the same, you can estimate all the main effects of the 5 input factors equally well. And therefore, this particular OMARS design belongs to that category of uniform precision OMARS designs. So that's the very first example of an OMARS. Now, after our first discovery of OMARS designs, we kept on working hard to find more OMARS designs. And one of the things we did was we relaxed the requirement that every column should have the same number of zeros. So we relaxed the requirement that the designs had to be uniform precision OMARS designs. So we allowed different numbers of zeros in the various columns. And technically speaking, that means that we started to create also non-uniform precision OMARS designs. Extreme cases of that are OMARS designs in which certain columns do not have any zeros at all. These specific OMARS designs we call mixed level OMARS designs. And why is that useful? Why is that useful to have columns without any zeros? Well, sometimes in an experimental study, a certain input is not quantitative. If that input is not quantitative and it has two possibilities, then a quadratic effect makes no sense, obviously, and then it's enough to have two levels for that particular input. So these mixed level designs, yeah, they do make sense in certain applications. And what also happens, we will see that in a case study that I will discuss later, is that sometimes researchers do not care about certain quadratic effects. Then it makes no sense to study the corresponding input factor at more than two levels. So that's why we paid attention to that special case where certain columns do not have any zeros. Now, with improved algorithms and by allowing non-uniform precision OMARS designs, we immediately found many more OMARS designs. And this particular table gives you a flavor of how many OMARS designs we found. The different rows in this table correspond to the number of tests in the experimental plan. So you see that we found OMARS designs with 14 tests, but also OMARS designs with 40 tests, and basically every number in between. This table only contains the even numbers, but there's also OMARS designs with odd numbers of tests. But then my table would become too long. And the columns in this table indicate how many input factors are included in the experimental plans. Well, you can see that for certain numbers of tests and certain numbers of factors, there's an awful lot of OMARS designs. For example, there's more than 1 million OMARS designs with 28 tests to study 6 factors. There's 27 million OMARS designs with 30 tests for 6 factors. So basically, that new family of experimental designs is incredibly big. Now, an important thing to know is that not each of these experimental plans is equally good. The big question that immediately comes to mind, of course, here is, of these millions of OMARS designs, which ones should I use for my experiments? Which ones have the best technical, the best statistical properties? Well, we performed a very thorough study of all these experimental plans that we discovered. Basically, every criterion that exists in the design of experiments literature to quantify how good or how bad an experimental plan is, every criterion we checked. So for these millions of designs, we basically know all their strengths, all their weaknesses. And then, of course, we hope to use that information, or we did use that information to recommend the best of these millions of OMARS designs. In our technometrics paper, we describe a procedure to select the best OMARS designs from that catalog of all the existing OMARS designs. And a key feature of our selection procedure is that it takes into account multiple criteria, multiple quality criteria for the experimental plans. That's a little bit a break with the tradition in design of experiments. In design of experiments, there is a paradigm, optimal design of experiments, where you use the computer to generate tailor-made designs. And these tailor-made designs are always constructed by optimizing exactly one criterion to measure the quality of an experimental plan. So you could say that's a sort of one-sided approach to design of experiments. We wanted to avoid that here, We wanted to have a multi-criteria decision tool to select the best possible experimental plans. And our procedure involved, yes?
I think
Yeah.
we are now at 2 p.m. So
Yeah.
do you want to finish this part and then have the break, or should we stop here and then talk about the multi-criteria after the break?
I think we can talk about the multi-criteria after the break.
All right, great. So everybody, let's have a 5-minute break. So we have around 1 more hour left. And I would like to just also open the floor for questions if there are any about the first part of the material. After we come back from the break, I will release the registration form, so you can register and then you can get a certificate of participation in the tutorial. All right, so the 5 minutes, they start from now. All right, so that's 5 minutes. So let's continue. As I said, I will leave the registration form in the chat in a moment. I also would like to kindly ask if you have any questions. I would like to ask one question myself while you think about any questions you might have. Peter, so you mentioned that this response surface methodology and these designs, well, they have been here for quite a while, and we now have definitive screening designs since 2011, and now OMARS designs. Is it time to revisit the way that we teach experimental design? So do you think that we must now include DSDs in an experimental design course and OMARS designs as well?
Yes, I'm indeed convinced that probably textbooks should be revised a little bit to take into account the fact that we live in the 21st century. First of all, we no longer need to do data analyses by hand, so that, absolute desire to have perfect orthogonality, that's less important than it used to be. Another thing is that there's nowadays much more flexible ways to design experiments. Many industries are under enormous pressure to innovate quickly, efficiently. And the large experimental designs from the past don't help to do that. So they scare away people from systematically investigating their inputs. So I think indeed, we need to teach our students about the existence of modern technology.
All right. Thanks. And well, if there are no questions, so let's continue then.
So I stopped after saying that we turned our large catalog of OMARS designs inside out. We quantified their strengths and weaknesses in all kinds of ways. And that information we use in a multi-criteria decision selection, design selection algorithm. In our original Technometrics paper, we framed that as a 3-step approach. There's a satisficing stage, a dominance stage, and then a final selection stage where you can use the utopia method or where you can do a manual design selection. The satisficing stage is where you do a rough filtering, basically, of all the OMARS designs that are available. So in that stage, you select designs that meet certain minimum quality criteria. After doing that, after getting rid basically of the designs you absolutely don't want, we enter the dominance stage. And in the dominance stage, you discard all the designs that are dominated by others for whatever subset of design characteristics that you have in mind. In operations research jargon, that's basically the phase where we select the Pareto front of all the possible designs. And then in the final step, out of all the OMARS designs that belong to your Pareto front, you need to make a wise selection. And you can do that in various ways. If you're an expert in design of experiments, you maybe want to do that manually. But if you're not so much an expert in experimental design, you may want to use the utopia method to sort of automatically select one design from the Pareto front. And the Utopia method, works as follows. It compares all the designs on the Pareto front to a fictitious design which has the best possible characteristics of all your designs on the Pareto front, and the design that is the closest to that fictitious design, that's the design that you eventually recommend, or the design that you eventually select. So that's basically what we described in our technometrics algorithm. At that point in time, my co-author, Jose Núñez Ares, he made a prototype web-based software to make this kind of design selection from the catalog of OMARS designs. After, developing that prototype, Jose, with my help and with the help of others, established a spin-off company from the University of Leuven to valorize, to commercialize the OMARS designs and that software. And what happened in February this year is that the spin-off company, FX, as it was called, has been taken over by Minitab. And now the software developed within the spin-off FX, which is short for efficient experimentation, by the way, that web-based software is now available in the Minitab Solution Center. In the Minitab Solution Center, which is part of the core version of Minitab, there's a tile where you can access the web-based software from FX. So that's brand new information. So the takeover was in February. And since last Wednesday, so 2 days ago, the FX solution is available in Minitab. So, and of course, the prototype software from a couple of years ago, from the time of the technometrics paper, has evolved substantially. It's become much more powerful. And here you can see some screenshots of this web-based software where you can clearly see a tile that leads you to the OMARS designs. And this is part of the user interface here. You need to say how many factors you want to study at 3 levels, how many factors you want to study at 2 levels. And from there on, you can basically go through that satisficing stage, that dominance stage, and that recommendation stage with the Utopia points method. So all of that has been embedded in a user-friendly user interface. So that basically brings me to the introductory part, to the end of the introductory part of this table. So I've shown you that we have that brand new catalog of orthogonal designs, the OMARS designs, where there's a lot of flexibility in terms of the number of tests that you can perform. In my opinion, these OMARS designs are especially useful if the number of tests you can afford is too small to estimate all the main effects, all the interaction effects, and all the quadratic effects at the same time. So the OMARS designs are especially useful, I think, if you're under time pressure, if testing is expensive, labor intensive, and if you have a lot of input factors to study. And because we have that complete catalog of OMARS designs, you can basically select the best possible OMARS design for your particular application based on multiple criteria, as we've seen. Now, multiple companies, of course, have already been using OMARS designs, and I brought a couple of slides of some of the first applications of OMARS designs in industry. The first example that I brought today comes from GSK, a vaccine manufacturer. So they have become a big fan of OMARS designs. And one of the evangelists for OMARS designs within GSK is Bernard Frank. And yeah, he's very fond of the OMARS designs, especially because they allow you to do a screening experiment and a response surface experiment in one. So what you're seeing here is a screenshot basically of one of the slides of Bernard when he presents at conferences about the OMARS designs. So he especially likes the fact that you can do one experiment instead of two whenever developing a new vaccine. Yeah, therefore you save a lot of time and a lot of costs. In the slides that I brought today, it's about OMARS design to study 6 input factors. You can see the names of the 6 input factors being listed here. So these are the names of the 6 input factors, 6 quantitative input factors. The output was the amount of biomass that they produced. And for this particular experiment, they are using a technology which is called the AMBER 250 system. That's a system involving 24 little bioreactors. And in these 24 little bioreactors, each of which can contain 250 milliliters, in these 24 bioreactors, they can test 24 combinations of these 6 inputs at the same time. So they can do 24 tests basically in parallel, very, very efficiently. So what they needed was an experimental plan for 24 tests. And they were interested in all the main effects, all the quadratic effects, and all the interaction effects. And if you add up all the effects that they are interested in, there's 28. So basically, they wanted an experimental plan with fewer tests than the number of effects that they were interested in. And that is basically the ideal situation for OMARS design to be used, in my opinion. Here, by the way, you see a picture of that AMBER 250 device. So here you can see, the little bioreactors standing next to each other. There's 24 of them in total, and in each bioreactor, individual test is going on. Yeah, GSK has been using the software to select the OMARS designs themselves. And yeah, they picked an OMARS design with 24 tests. They deliberately picked an OMARS design with replicates so that they could get a model-independent estimate of the variation in the biomasses produced. So the design selection procedure also has an option to indicate, yeah, I want an OMARS design with a couple of replicates. And there are quite a few OMARS designs that do have replicates. There's also quite a lot of OMARS designs that do not have. So that's one application of an OMARS design here. At the end of the day, after the experiment, the researchers found out that 4 of the 6 input factors had significant effects. And they used the effects software also to optimize their system. So to find those settings of the inputs, the 4 inputs that matter significantly, they identified the settings of these to maximize the amount of biomass produced. And some of the inputs had a quadratic effect, hence the curves. Some other inputs did not have a quadratic effect. So that's where you see a straight line visualizing the effects of the speed pump and the pH. These have linear effects in this particular application. So GSK is one of the companies that has been using OMARS designs already. Another company that has been using OMARS designs is W.L. Gore, chemical company. And W.L. Gore's applications of OMARS designs are very different from those of GSK. So at GSK, they have that AMBER system, which basically stands in their laboratories. W.L. Gore's experiments don't take place in their laboratories oftentimes, but they take place at full production scale. And of course, if you're experimenting at full production scale, you also want to keep the number of tests limited. So W.L. Gore also had that, incentive to use small experiments such as. And within W.L. Gore, this is the evangelist for OMARS designs. That's Maria Lanzerat. She's been using several OMARS designs already. The application about which we're writing a paper, by the way, is about a 3-step production process where the first step involves a polymerization, the second step involves a coagulation, and the final step involves drying. In the experiment we're going to write a paper about, there are 8 input factors in total, some of which are confidential. And in this particular application at W.L. Gore, the researchers my pointer got stuck and I flew out of the presentation mode. I hope I'm back now. You can see my slides again.
Yes.
What I wanted to highlight was that a specific desire at W.L. Gore was to study certain input factors at 3 levels and other input factors at 2 levels. That's because they had been doing several experiments in the past already, and they sort of knew that for some factors there would be a nonlinear effect, and for other factors there would be a linear effect. So what they needed was an OMARS design where certain columns had no zeros, only -1s and +1s, so 2 levels, and other columns had to have zeros besides the -1 and the +1, so certain columns had to have 3 levels. So that was very specific in this application, and the OMARS design that W.L. Gore used is this particular OMARS design here, where you can see that some columns are colored light blue. These are the columns that have 3 levels, where you find some zeros, obviously. And the dark blue columns are the columns that don't have any zeros. So they have 2 levels only, a low level and a high level. So that's a very different OMARS design than the one of GSK. But it also has 24 tests, but for different reasons, they didn't have an AMBER system, but they had to perform tests at full production scale. So that's why they wanted a small experimental design for 8 factors. So you can see that you can study 8 input factors in just 24 runs with an OMARS design. So that's the 2 case studies that I brought today. I can say that OMARS designs have been used in the meantime in the food industry, in the energy sector, various companies, especially I should say pharmaceutical and chemical companies have been using OMARS designs, but there have been spillovers to other industries as well. Now I want to come back to some other contributions we made in the OMARS in the OMARS field, one of the things that happens when you're experimenting is that sometimes you have to split your experiments in pieces or in subsets of tests. And yeah, in the experimental design jargon, we say that you need a blocked experiment. When does that happen? Well, oftentimes you cannot execute your experiment in one day. You have to split your experiment over multiple days. Sometimes you have 5 operators who are going to do a couple of tests. So in all those cases, you have like subsets of performed on different days or performed by different operators. And then you need to take these OMARS designs and sort of divide them in subsets. We also did research about that. We also used basically linear programming techniques from operations research to make the wisest possible subdivisions of your OMARS designs. And yeah, to publish a paper about that topic, we had to prove that our linear programming approach in combination with OMARS works well. And yeah, we compared our blocked OMARS designs to blocked definitive screening designs extracted from the JUMP software. What you see on the current screen is a definitive screening design with 5 factors. And the definitive screening design is subdivided in 5 sets of 5. So that means that this particular experimental plan is intended to do 5 tests during 5 days, or to have 5 operators who each execute 5 different tests. Now that's the blocked pattern of a definitive screening design that came out of JUMP, our benchmark. Now we picked the best possible OMARS designs that we had in our catalog, and we subdivided our catalogs also in 5 sets of 5 tests. So here you can again recognize the subdivision in 5 groups of 5, in the jargon, 5 blocks of 5 tests. Now, this subdivision, yeah, it's optimized using linear programming so that we learn as much as possible from the blocked OMARS design. And yeah, when do you learn as much as possible? If day-to-day variation or operator-to-operator variation impacts your results as little as possible. And to do that, you must make sure that the average level of every X is equal to 0 in every block. And you can see here that I highlight particular columns within a group, within a block. And when you look at the 5 values in these red frames, you can see that they always average to 0. That is true for every X in every block in this particular arrangement. So that's one of the technical things we achieved with our linear programming technique. What we also did was we tried to make sure that there was as little correlation as possible between the cross products of the X's and the blocks, and also as little correlation as possible between the squares of the X's and the blocks, so that we learn basically as much as possible about the interaction effects and the quadratic effects as well. Well, it turns out that this linear programming technique that tries to achieve that works very well, because if we compare our blocked OMARS designs to blocked definitive screening designs, yeah, the OMARS designs are almost always very clear winners. For example, the current little table that I show you shows the standard errors for estimating main effects and quadratic effects from that blocked experiment with 25 tests in 5 blocks of 5. So you can see that the main effects have a smaller standard error with the OMARS designs. So that means you can estimate the main effects better, a little bit better, I should say. When it comes to the quadratic effects, you can see that the quadratic effects have a much smaller standard error. So the quadratic effects are estimated much better with the OMARS design than with the definitive screening design. And I have a picture to show you the standard errors for the interaction effects. At the bottom, we have these bullets here. They indicate the standard errors that you get from the definitive screening design for the interaction effects. Right here on the left-hand side, you see the bullets showing the standard errors for the very same interaction effects when you use the OMARS design. And you can see that the bullets for the OMARS design lie much more to the left than the bullets for the definitive screening design, so that the OMARS design gives much better information about the interaction effects than the definitive screening design. So summarizing this slide, basically, for every kind of effect, the blocked OMARS design does better than the blocked definitive screening design. So, and I suppose that the informs public that I have here today should be very pleased to hear that operations research techniques such as integer programming, linear programming, turns out to be very useful to create OMARS designs on one hand, but then also to arrange the OMARS designs in blocks for cases where you cannot do all the tests on one day or with one operator. So blocked OMARS designs are also very good. And that brings me to the next topic in this presentation. Coming up with an experimental plan is one thing. Executing the experiment then is another thing. And at the end of the day, you have to analyze the data that result from your experiment. And that's where you basically try to build that statistical model, the kind of statistical model that I showed you in the beginning of the presentation. You need, from your limited data, you need to try to find the best possible model or models for your data. And the technique that we use in the FX software, so now in Minitab DOE by FX, the technique that we use is inspired by a paper by our host today, Alan Vasquez. He came up during his PhD, he came up with a very specific technique, also based on operations research, to analyze data from small experiments with quite a lot of input factors. How to frame this analysis? Well, when you've done an experiment that has limited number of tests and quite a lot of input factors, your data analysis is certainly not going to be super easy. And what we have often observed is that among all possible models that you can build, there is rarely a clear winner. And that basically inspired us to look at multiple models instead of putting all our money on a single model. And what is the best known technique in regression courses to consider multiple models? Well, the best known technique is a technique called all subset regression. All subset regression is available in many software packages. And it's very intuitive. All subset regression means you're going to build all models with one term, all models with two terms, all models with three terms, and so on and so on. And you're going to compare all these models in terms of multiple goodness of fit criteria, as we call them, in terms of multiple criteria to quantify the quality of your models. The problem is that a literal implementation of all subset regression is computationally very hard. And if you have a lot of input factors with a lot of interaction effects and a lot of quadratic effects, that literal implementation of all subset regression can even become computationally infeasible. So it's a simple strategy to explain, but it's not always simple to implement all subset regression in practice. And that's where, Alan and his supervisors called operations research to the rescue. It turns out that if you use a mixed integer optimization, you can actually carry out an all subset regression without literally enumerating all possible models. And thanks to the magic of mixed integer programming, basically, you can still be sure that at the end of the day, you have found the best possible models for your particular data set. So basically, for the third time today in this tutorial, we use operations research techniques in a statistical context to move forward basically in an efficient way. Where did the inspiration to do that come from? Well, in the annals of statistics 10 years ago now, there was a paper by Bertsimas, King, and Mazoum there about using best subset selection through a modern optimization lens. We basically took their approach and we tailored it to the typical small experiments that we often observe in industry. The mixed integer program is shown here, but just like for the system of linear equalities in the beginning of this talk, I will not discuss this mixed integer program in detail. You can read more about that in our paper in Journal of Quality Technology, also from a couple of years ago. So a key feature of this approach is that we come up with a list of good models rather than just with one good model. Now, of course, if you come up with a list of models, it's a little bit hard to summarize all your results. Well, we came up with a graphical approach to summarize basically all these models. And that graphical approach is sort of heat map. But we call it a raster plot because the original authors who used that ID, Walters and Bingham, in a paper in Technometrics, they didn't call their graph a heat map, but they called it a raster plot. The original raster plots in the Walters and Bingham paper, as well as in our own paper, they were just static pictures. But of course, if you implement that ID in modern software, you can make these raster plots interactive and colorful. So in the Minitab DOE by FX software, these raster plots have come to life basically. You can hover with your mouse over these graphs, and you can basically read about the meaning of all these graphs. Here's a raster plot from a data analysis that I did in that software. So in that raster plot, you see a horizontal axis and a vertical axis. The vertical axis basically has the numbers of all the good models identified by that mixed integer optimization approach. On the horizontal axis, you basically have all the effects that might be important in your model. It starts with main effects, then you have interaction effects, and finally you have quadratic effects. And the idea is, if the column corresponding to a certain effect is completely colored, that effect is present in every model. And you can see that for some of the main effects, the entire column is almost colored. And that basically means that these main effects are certainly important because they appear in each of the 100 and something good models identified by the mixed integer programming approach. Some other effects, interaction effects, quadratic effects, some other effects have a column that's almost entirely white. And these are effects that never pop up in any good model. So we can safely conclude that these effects are then unimportant. So that's a raster plot. Now, in the software, you can then filter these models and eventually get one recommended model if you want that. The filtering of models is based on basically the traditional criteria for goodness of fit. The R-square is there, the coefficient of determination, the adjusted R-square, Akaike's information criterion, the Bayesian information criterion. All of these criteria are calculated for each of the good models visualized in the raster plot. And then you can use a graphical tool, a parallel coordinate plot, to filter the models. You can select models with a low value for the Akaike information criterion, a low value for the PRESS, the prediction error sum of squares, a high value for the R-square. So you can basically use this tool, the parallel coordinate plot, in which every line here corresponds to one of the models. So by basically selecting models on these vertical axes here, you can basically select a limited subset of very good models, taking into account your favorite goodness of fits. If you do not like to do that yourself, narrow down, to a very limited, to a short list of models. The software also has the possibility to get a recommended model. And then basically the utopia point method is again called to select the best possible model with respect to all of these criteria that you see here. So we believe that this is a very comprehensive analysis of the data from an OMARS design. So basically you have a lot of good models, you turn them inside out to see all the qualities of these models, and eventually you can use a multi-criteria decision tool to select the best or the 3 best or the 5 best models for your data. And these 3 best, 5 best models you can then use to figure out what X values, what input combinations you need to select to get the desired output for your system. And that brings me to the end of the presentation. So I gave you a very quick 95 minutes, maybe 100 minutes overview of traditional design of experiments, more modern design of experiments, and then especially the new family of designs, OMARS designs, to combine screening experiments and response service experiments in one. And by doing that, you can save precious time in product and process development. So that's it. I
All right.
welcome every possible question.
Thank you. Thank you very much, Peter, for this very informative tutorial on modern experimental design. So from completely randomized multifactorial designs, then going through block experimental designs, and now as well as analysis. So now let's open the floor for questions about the tutorial about experimental design. So you can either put them in the chat and I can read them out loud, or if you would like to raise your hand and ask yourself, please feel free to do so. So while people think about potential questions, I have another one. So you show that for a specific number of runs and factors, we have many OMARS designs, and there are several statistical criteria that you can use to narrow down the list. And then at the end, you will have many, maybe 2 or more experimental designs on the Pareto front. Then the question is, how would you choose, or what have you seen in the applications of OMAR designs? What have you seen as a rule to select the very final design?
But the very final design is certainly strongly based on the power to detect effects.
Mm.
So you certainly want a high power to detect main effects, direction effects, and quadratic effects if they exist. Another thing that we like to look at is the variance of predictions. So what you want at the end of the day are good statistical models that can predict what happens whenever you pick a certain input combination. So what we want is low prediction variances as well. Some people also want to have replicates in their experimental plan. If you have a limited number of tests, I'm not a big fan of that approach because the main reason why you do the experiment is generally to learn about the effect of the input factors, and having replicates doesn't help to identify these effects. But yeah, it's a very intuitive way, replicates, to have to learn about the random variation in your system. But yeah, most people don't do an experiment to learn about the random variation in their system. They want to detect the systematic effects. So powers, of course, the number of tests alone is a very important one as well in the final selection of design. Oftentimes there's a very strict budget limits. So that's also a main criterion in the selection.
So any questions from the audience? Yeah, so we have one question in the chat. So, hi, Peter, this was a wonderful presentation. Well, it was kind of like a compliment. Thank you for speaking slowly and clearly. I can't remember the last time I could really follow a presenter live, so thank you for that. From Patrick. Thanks.
You're welcome.
Oh, I have a question, if I may.
Yeah, go ahead, Bill.
So I'm curious, like for constructing these OMARS designs using the mixed integer programming approach, I'm curious how well does this scale, does it scale in terms of the number of factors? Like I can imagine that the mixed integer programs get very large like in terms of the number of decision variables as you increase the number of factors.
Yeah, that's true. What I did not discuss is the computing time. So we had to use supercomputers. Yeah, we had to use the fanciest techniques to speed up the solution of these systems of linear equalities. So yeah, it doesn't scale very easily, but the nice thing is you only have to do that once. Once you have the catalog of OMARS designs, of all possible OMARS designs, you're done. There's no need to do that exercise again.
I see.
So, and yeah, we're now several years after the publication of our first technometrics paper. During all these years, computations were running and we continuously expanded the set of OMARS designs. We have bigger and bigger OMARS designs for more and more factors in the meantime.
I see. Thank you.
Yeah, but of course, if I would want to do it again, yeah, starting from scratch, yeah, it would again take a couple of years before we have the same set of OMARS designs.
Thank you.
So we have another question from Israel. So Israel, go ahead.
Hi, doctor. I have a question.
Sure.
What do you think about using artificial intelligence to select a experimental model, design of experimental model, for example, to elevated to N? What do you think to use the artificial intelligence like Cloud or Gemini to select the correct this design of experimental model?
Yeah, we have tried that as well. So there's all kinds of approaches that you can use to select clever sets of test combinations. But so far, with faster techniques from operations research and within the framework of artificial intelligence, yeah, we have been unable to generate test combinations that are equally good as the ones that we have currently. So we've been using, for example, our OMARS designs as training material for all kinds of artificial intelligence models, but so far you cannot generate bigger OMARS designs from smaller ones, for example, with artificial intelligence techniques. So it's always less informative test combinations that you get. And given that, for example, at W.L. Gore, these individual tests were so expensive, yeah, you certainly want to have the best possible test combinations and not mess around with suboptimal test combinations.
So yeah, so we have another question from Patrick. Have you considered an ensemble approach to model fitting versus the all possible subsets approach? What would be the benefits of doing that over this Mayo approach with all possible subsets? And he follows up, so I'm going to read it. I was thinking that perhaps the all subsets approach that you have used might be better for model explanation, but that the ensemble approach might be better for prediction.
Yeah, that's something that we have considered indeed. Well, with the Mayo approach, we wanted to do something that's very close to what everybody knows from his or her regression courses. So therefore, we thought that's an easy sell. But yeah, you're right that when you have model uncertainty, when you don't know what the best possible model is, you may want to proceed with multiple models and do some model averaging, for example, to make predictions. So I would certainly be in favor of that, as an alternative technique for identifying optimal input combinations that give you the desired output. I think that kind of approach should be used more often, perhaps, rather than putting our money on one winning model. You should accept the fact that you doubt between multiple models and use something more general. But indeed, I think you mentioned the term model explanation in your question. Yeah, that's something that we observe quite often, that people want to understand what's going on. So they sort of want to see the effects of the individual inputs on the output.
So we have time for one more question. All right, so I think if there are no more questions, so we can end up here. So Peter, thank you very much. I'm going to stop the recording. So thanks for everyone who connected and for
You're
everyone
welcome.
who is watching.